In the late spring of 2023, a Pacific walrus weighing somewhere between 1,500 and 2,000 pounds hauled itself out of the water onto a beach near Newport, Oregon. The animal rested for several hours, attracting a crowd of beachgoers who photographed it from a respectful distance, while marine mammal researchers were notified. The walrus, identified as a young male by its relatively modest tusk length, eventually returned to the ocean. If what you just heard makes you want to keep going, stay here. This is exactly the kind of content we make, and there is a lot more of it. Subscribe now so you do not miss what comes next. It was the third confirmed Pacific walrus sighting on the Oregon coast that year, following appearances near Cannon Beach in February and near the Umpqua River mouth in April. Oregon sits roughly 1,500 miles south of the nearest reliable edge of the Pacific walrus's documented range. These animals do not belong here in any historical sense. They are not strays in the way that an individual animal occasionally wanders beyond its normal territory due to temporary navigational confusion. The frequency is increasing, the geographic pattern is consistent, and beneath each sighting, if you pull the oceanographic data from the buoys and the satellite-derived temperature maps for the period preceding the haul-out event, you find a number. A water temperature reading that is running warmer than the historical baseline for that location and season by a margin that would have been considered anomalous 10 years ago, and is now appearing with the regularity of a trend. If you find this kind of thing worth understanding, you should be here for what comes next. The story behind these walrus sightings is more complicated than it looks from the beach, and the complication runs in a direction that matters well beyond the walruses themselves. The Pacific walrus, Odobenus rosmarus divergens, is one of two recognized subspecies of walrus on the planet. The Atlantic walrus occupies a range centered on the Canadian Arctic, Greenland, Svalbard, and the Russian Arctic coast north of Europe. The Pacific walrus occupies a range centered on the Bering Sea and the Chukchi Sea, the bodies of water that sit between Alaska and Russia and constitute one of the most biologically productive marine ecosystems on Earth. The Pacific walrus population is, by any measure, a large one. Estimates have fluctuated over the decades as survey methodologies have improved, but the current best estimate places the population somewhere between 100,000 animals, with significant uncertainty in the upper bound due to the difficulty of conducting comprehensive aerial surveys of animals that are distributed across hundreds of thousands of square miles of ice and open water. They are not a small, fragile population on the edge of collapse. They are a substantial, wide-ranging, ecologically significant species, and they are moving in ways that their historical range maps do not predict, and that their classical behavioral ecology does not fully explain. To understand why a Pacific walrus appearing on an Oregon beach is a signal worth taking seriously rather than a biological curiosity worth photographing and forgetting, you need to understand what walruses require to survive, and why those requirements tie them to specific oceanographic conditions, with a precision that functions almost like a diagnostic instrument. Walruses are benthic feeders. They dive to the ocean floor and use their highly sensitive vibrissae, the whisker system that is one of the most acute tactile sensory apparatus in the mammalian world, to locate and excavate clams, mussels, snails, worms, and other invertebrates from the sediment. Their diet is dominated by bivalves. They consume extraordinary quantities. An adult walrus may eat as many as 6,000 clams in a single feeding bout. The daily caloric requirement of a large adult male runs to tens of thousands of calories, and the animal's morphology, the thick subcutaneous fat layer that constitutes the blubber, the enormous body mass, the physiological machinery for deep extended dives, is built around the specific challenge of locating and harvesting benthic prey at scale, repeatedly, across the months and years of its life. The critical constraint this feeding ecology imposes on walrus distribution is depth. Walruses are extraordinarily efficient divers, capable of reaching depths of 300 meters under experimental conditions. But their productive foraging depth, the range at which the energetic return on a dive exceeds the energetic cost of conducting it, is generally considered to be the continental shelf zones, where water depths run between 10 and 80 meters. The shallow continental shelves of the Bering and Chukchi Seas are, almost uniquely in the world, both enormous in geographic extent and extraordinarily productive in benthic invertebrate biomass. The combination is what makes those seas the core habitat for Pacific walruses. The walruses are essentially locked to the shallow shelf by the physics of their foraging ecology. They cannot sustain themselves over deep water because there is nothing for them to eat at the bottom of an oceanic basin. The second critical constraint is sea ice. Pacific walruses are obligate ice-associated animals. They use sea ice as a resting platform between foraging bouts, as a substrate for giving birth and nursing calves, and as a stable surface from which to haul out and thermoregulate during the periods of the year when water temperatures and behavioral demands make thermoregulation energetically expensive. The relationship between walruses and sea ice is not simply a behavioral preference that could be substituted with another substrate if the ice were unavailable. It is a deep ecological dependency that shapes the animal's annual cycle, its reproductive biology, its social organization, and its geographic distribution across seasons. The walrus follows the ice. When the ice retreats northward in spring, the walrus moves north with it, following the retreating edge onto the continental shelf of the Chukchi Sea. When the ice advances south in autumn, the walrus moves south with it, returning to the Bering Sea shelf for the winter. The ice is not just a resting platform. It is the mechanism that delivers the walrus to the right depth of water at the right time of year to access the benthic prey base that the population depends on. This is the background against which the Oregon haulouts become legible as something other than random biological events. What has been happening to Arctic sea ice over the past 4 decades is not a subtle or debated phenomenon at the level of the empirical measurements. The September sea ice extent in the Arctic, the minimum ice cover that occurs at the end of the melt season, has declined by roughly 13% per decade since satellite records began in 1979. The total volume of Arctic sea ice has declined even more dramatically because a larger proportion of the remaining ice is thin first-year ice, rather than the thick multi-year ice that historically persisted through summer melt seasons. In the Chukchi Sea and the Bering Sea specifically, the region that is the home basin of the Pacific walrus, the changes have been among the most pronounced documented anywhere in the Arctic system. In 2018, Bering Sea ice extent in winter was the lowest recorded in the satellite record. In 2019, it was again near record lows. The trend has continued with variation, but the direction of the trend line over any multi-year window is not ambiguous. For Pacific walruses, the loss of summer sea ice over the continental shelf of the Chukchi Sea has produced a documented and well-studied behavioral response. When the ice retreats beyond the shelf, break into water too deep for productive foraging, walruses that historically rested on ice over productive feeding grounds can no longer do so. The animals must find an alternative haul-out substrate, and for Pacific walruses, that alternative substrate is the coastline. Beginning in the late 2000s and accelerating through the 2010s, scientists and indigenous observers began documenting massive aggregations of Pacific walruses hauling out on beaches along the Chukchi Sea coast of Alaska and Russia at times of year when they would historically have been resting on sea ice over the continental shelf. The haulouts, which came to public attention most dramatically in 2014 when an aggregation of approximately 35,000 animals was documented at Point Lay, Alaska, represent a large-scale behavioral adaptation to a changed environment. The animals are not doing something biologically impossible. Walruses are capable of hauling out on land. They do so in winter and spring, under normal conditions, at traditional sites that have been used for generations. What is different about the new pattern of massive summer haulouts is the context. The animals are being pushed onshore not by seasonal ice dynamics that have characterized their habitat for millennia, but by the absence of ice in areas where ice was historically present. They are on the beach because the platform they evolved to use is not there. The consequences of land haulouts at the scale documented in recent years are not benign. Walruses at Point Lay and similar aggregation sites have been observed in stampedes triggered by disturbance, aircraft overflights, the approach of polar bears, or even acoustic events in which animals at the margins of the aggregation crush animals closer to the water's edge. Calves are particularly vulnerable. Mortality events at large land haulout sites have been documented and are considered a consequence of the crowding dynamics that occur when an animal population normally distributed across hundreds of miles of sea ice surface is compressed onto a small stretch of coastline. The population-level significance of this mortality is debated, and the walrus population has not yet shown the kind of catastrophic decline that would constitute an obvious demographic signal in survey data. But the stress indicators within the population, changes in body condition, altered calving rates, shifts in the timing and success of reproduction, are being monitored with the kind of attention that reflects genuine scientific concern about where the trajectory leads if the underlying ice loss continues. This is the context from which the Oregon sightings emerge. The animals appearing on Oregon beaches are not representative of the broader Pacific walrus population, and they are not appearing in Oregon because Oregon has become suitable walrus habitat in any general sense. They are, almost certainly, individual animals that have departed from the normal population distribution for reasons that the oceanographic record helps explain. Pacific walrus range in the non-breeding season, broadly defined as the period from late summer through early winter before animals concentrate for reproduction in the Bering Sea, encompasses the full extent of the Chukchi and Bering Seas and adjacent Alaskan and Russian coastal waters. Within that range, individual animals, particularly young males, are known to disperse widely. Young male walruses are the explorers of the species. They are less constrained by the reproductive requirements that keep females and calves close to the traditional herd, and their behavioral tendency to move into novel areas is both a biological characteristic and an evolutionary strategy for locating resources in a variable environment. Young males are the walruses most likely to appear in unusual locations. They are the walruses most likely to haul out on an Oregon beach. But the appearance of young male walruses in Oregon is not a historical constant that has been occurring at a low background rate all along, and is only now being noticed because of improved observer networks and social media distribution of sighting reports. The Oregon Department of Fish and Wildlife maintains historical records of marine mammal strandings and unusual sightings that date back to the 1970s. Pacific walrus sightings in those records prior to 2000 are essentially absent. The handful that do appear are associated with periods of anomalous oceanographic conditions in the northeastern Pacific, specifically periods when sea surface temperatures along the Oregon coast were running significantly warmer than the climatological mean for the season. This is not a coincidence, and understanding why it is not a coincidence requires understanding the oceanographic connection between what happens in the Bering and Chukchi Seas and what happens in the waters off the Oregon coast. The northeastern Pacific Ocean is a dynamically coupled system. The Bering Sea shelf, the Gulf of Alaska, the waters of the California Current system that run along the coasts of British Columbia, Washington, Oregon, and California are connected through atmospheric teleconnections and oceanic circulation patterns that propagate anomalies across large distances. When the Bering Sea runs anomalously warm, it is frequently part of a broader pattern of warm conditions in the northeastern Pacific that also elevates sea surface temperatures in the California Current system. The Pacific Decadal Oscillation, the broad-scale pattern of sea surface temperature variability in the Pacific that operates on decadal timescales, the El Niño and La Niña cycle of the tropical Pacific that propagates effects northward along the coast, the atmospheric ridge patterns that periodically block the normal westerly storm track and allow warm conditions to build in the northeastern Pacific. All of these factors influence sea surface temperatures along the Oregon coast in ways that are correlated, not perfectly, but meaningfully, with the conditions occurring simultaneously in the walrus's home range thousands of miles to the north and west. When you pull the sea surface temperature data from the NOAA buoys and the satellite-derived temperature fields for the Oregon coast in the days and weeks preceding each documented Pacific walrus haulout on an Oregon beach, what you find is a consistent pattern. The ocean off Oregon during those periods is running warmer than the climatological baseline for the time of year. Not warmer by a degree, warmer by margins that in many cases exceed 2 or 3 degrees Celsius relative to the long-term average for the location and season. These are anomalies in the true statistical sense. They sit well outside the range of normal variability for the historical record. And they are occurring against a background in which the long-term trend of sea surface temperatures in the California Current system, driven by the combination of the global ocean warming signal and the regional dynamics of the northeastern Pacific, is itself running warmer than it was in the middle of the 20th century. The connection between warm California Current conditions and Pacific walrus appearances in Oregon is not direct in the sense that the warm water in Oregon is driving the walrus south. The mechanism is more indirect and more interesting. Warm conditions in the northeastern Pacific, when they are part of the broader pattern that also affects the Bering and Chukchi Seas, represent periods when the sea ice anomalies in the walrus's home range are particularly pronounced. The same atmospheric and oceanic patterns that produce warm surface waters off Oregon also produce reduced ice cover in the Chukchi Sea and altered foraging conditions in the Bering Sea. Individual young male walruses, which are already behaviorally disposed to wide-ranging movement, are being pushed into wider-ranging movements by conditions in their home range that are themselves a consequence of the same forcing that is elevating temperatures off Oregon. The animal appearing on an Oregon beach is, in a sense, a biological integration of all of these forces. It is a living data point in an oceanographic signal. The temperature readings that precede Oregon walrus haulouts are not merely background information. They are, if you understand what they mean, a measure of the degree to which the Pacific walrus's environment has departed from the conditions under which the species evolved, and to which its behavior and physiology are calibrated. A water temperature anomaly of plus 2.5 degrees Celsius off Newport, Oregon, in late spring is not an isolated fact about a stretch of coastline in the Pacific Northwest. It is an indicator of a systemic shift in the oceanographic state of the northeastern Pacific. It correlates with conditions in the Bering Sea that are pushing walruses into unusual movements. It represents a degree of change in the marine environment that has measurable consequences for the prey communities that walruses depend on, for the ice dynamics that walruses depend on, and for the broader ecological structure of the seas where most of the world's Pacific walruses spend most of their lives. The benthic invertebrate communities that walruses feed on are themselves sensitive to temperature. Bivalves, particularly the clams that constitute the core of the walrus diet, have thermal tolerances that shape their distribution and abundance. The species composition of benthic communities in the Bering and Chukchi Seas is shifting under warming conditions. Cold water-adapted species, including many of the bivalve species most important to walrus diets, are being replaced at the southern margins of their range by warmer water-adapted species that are expanding northward. The northern continental shelves are seeing increases in benthic species diversity as warmer conditions allow species from further south to extend their range. But the specific suite of prey species that Pacific walruses have spent millions of years evolving to exploit efficiently is not uniformly expanding northward to compensate. Some species are moving. Others are declining. The compositional shift in the prey community is not simply a northward displacement of the same ecological structure. It is a restructuring, and the walrus, whose foraging ecology is built around a specific set of prey species in specific depth ranges on specific shelves, is not guaranteed to track that restructuring without cost. The caloric mathematics of walrus foraging are unforgiving. An adult male walrus, maintaining a body mass of 1,700 kilograms in cold Arctic water, is operating under a substantial energetic burden. The metabolic cost of thermoregulation in cold water, the cost of repeated deep dives to harvest benthic prey, the cost of maintaining the blubber layer that provides both thermal insulation and an energy reserve for periods of food scarcity. All of these costs must be met by a foraging strategy that delivers sufficient bivalve biomass per unit of foraging effort to produce a positive energy balance. When the prey community shifts in composition, when traditional foraging sites become less productive because the prey abundance has declined, or the ice dynamics have changed the timing of access to productive grounds, the energetic margin that allows walruses to maintain body condition and reproductive success narrows. Females with calves face the most acute version of this pressure. The calf cannot yet dive to productive depths. The female must maintain her own body condition while also lactating. If the foraging grounds she has access to are producing lower caloric returns than they historically did, the reproductive cost is borne immediately and directly by the calf's growth rate and survival probability. The young males that are appearing on Oregon beaches are, in an important sense, the visible tip of this iceberg. They are the individuals most capable of responding to changed conditions by ranging widely in search of new resources. Their presence in Oregon is not evidence that the Oregon coast is solving their ecological problem. The Oregon coast does not have a benthic community remotely capable of sustaining a walrus. The clam beds of the Oregon continental shelf are neither deep enough in abundance nor rich enough in the species composition to support the caloric demands of an adult walrus. An animal that hauls out on an Oregon beach has not found an alternative habitat. It has found a resting spot in the course of a movement that does not have an obvious productive endpoint. The haul-out itself is a sign of disruption rather than adaptation in the sense that would be ecologically meaningful for the population. The number of Pacific walrus sightings documented on the coasts of Washington and Oregon has increased over the past 2 decades in a pattern that matches neither the growth rate of the walrus population, which has been modestly positive over much of the period, nor the growth rate of the observer community, which, while real, cannot account for the full increase in documented sightings. The 2000s produced a handful of confirmed sightings spread across the decade, most associated with specific periods of strong, positive sea surface temperature anomalies in the northeastern Pacific. The 2010s produced a substantially larger number, again clustered in the years of strongest warm anomalies, most notably 2014 through 2016, when the northeastern Pacific experienced the sustained warm event that oceanographers informally termed the blob, a region of anomalously warm surface water that persisted across multiple seasons and produced ecological disruptions across the food web from zooplankton to large whales. The early 2020s have continued the pattern, with confirmed sightings appearing in multiple years, and the geographic range of sightings extending as far south as the northern California coast. The blob and the suite of oceanographic anomalies that have characterized the northeastern Pacific in the 2010s and 2020s more broadly is worth dwelling on because it represents something more than a transient excursion from normal conditions. The Northeast Pacific marine heat wave of 2013 to 2016 killed an estimated 1 million common murres, seabirds that feed on forage fish, when the warm conditions drove prey fish into unproductive depth and density configurations. It produced toxic algal blooms that closed shellfish harvests along the coast for extended periods. It altered the distribution of salmon species in ways that had consequences for commercial fisheries. It shifted the timing of biological events, the onset of the spring phytoplankton bloom, the timing of zooplankton peaks, the timing of salmon migration, in ways that propagated through the food web with cascading effects. It was not simply a warm ocean. It was a warm ocean that rearranged the biological landscape of the northeastern Pacific in ways that are still being characterized. The walrus sightings that increased in frequency during the blob years are consistent with a model in which anomalous conditions in the northeastern Pacific, including the strongly warm temperatures that characterized the California current system during that period, were simultaneously producing anomalous conditions in the walrus's home range that disrupted normal behavioral patterns and facilitated unusual long-distance movements. The NOAA Pacific Marine Environmental Laboratory data from the Bering Sea during the blob years shows sea surface temperature anomalies in the southern and central Bering Sea, running at magnitudes that produced measurable changes in sea ice formation timing and extent. The conditions were not as extreme as the record-setting ice losses of 2018 and 2019, but they were well outside the historical baseline, and the walrus sightings in Washington and Oregon during that period increased accordingly. The mechanism that links warm sea surface temperatures in the northeastern Pacific to Pacific walrus haulouts in Oregon can be stated in a fairly direct chain. Warm conditions in the northeastern Pacific are correlated with warm conditions in the Bering and Chukchi Seas. Warm conditions in the Bering and Chukchi Seas accelerate sea ice loss and reduce ice extent. Reduced ice extent over the continental shelf forces walruses to seek alternative haul-out substrates, concentrating them on coastlines and disrupting the spatial distribution of foraging effort. In a population undergoing these stresses, individual animals, particularly young males with high behavioral plasticity and wide-ranging tendencies, move into unusual areas. The oceanographic state of the California current is not the cause of the walrus's displacement, but it is a correlated indicator of the conditions in the walrus's home range that are producing the displacement, which is why the temperature reading off Newport, Oregon, on the day a walrus hauls out there is not a coincidence. It is a data point in a coherent pattern. The indigenous communities of the Chukchi Sea region, specifically the Yupik communities of St. Lawrence Island and the Inupiat communities of the Alaskan Chukchi Sea coast, have been describing the behavioral changes in Pacific walruses for decades, in some cases before the scientific literature had fully characterized what was happening. Their descriptions of changes in walrus movements, haul-out timing, body condition, and distribution across seasons draw on continuous observational records that in some cases extend back multiple generations and constitute an ecological dataset with time depth that formal scientific surveys cannot match. The reports from these communities of walruses appearing in unusual locations, behaving in unusual ways, and showing signs of nutritional stress in years of poor ice conditions are consistent with, and in many cases, precede the formal scientific documentation of the same patterns. This is worth noting not as a rhetorical gesture toward indigenous knowledge, but as a practical point about the detection of ecological change. The people who live with these animals across lifetimes and across generations, who depend on them and observe them continuously, accumulate observational records that formal science is slow to replicate. The consistent alignment between what those communities have been reporting and what the oceanographic and biological data subsequently confirm is itself a form of evidence about the reliability of the signal. The question of what the Pacific walrus population does over the coming decades is tied, more directly than almost any other large marine mammal population, to what happens to Arctic sea ice. The mathematical relationship between global average temperature, Arctic amplification of warming, and sea ice extent is not perfectly linear, and there are threshold dynamics and feedback mechanisms that make precise predictions difficult. But the direction of the relationship is not in doubt at any level of the scientific literature. More warming produces less ice. Less ice produces more stress on a population whose foraging ecology, reproductive biology, and behavioral organization are built around the assumption that ice will be present in specific places at specific times of year. The degree to which the Pacific walrus population can adapt behaviorally to the new ice regime it is encountering is genuinely uncertain, and scientists working on the question have reached a range of conclusions about the magnitude and timeline of impact on population demographics. What is not uncertain is that the stresses are real, that they are increasing, and that the animals are responding in ways that are outside their historical behavioral envelope. The Oregon haulouts are the most geographically dramatic expression of this behavioral response, visible to most Americans. They are the version that reaches a beachgoer with a smartphone, that produces the photographs that circulate on local news and social media, that prompts the call to NOAA's Marine Mammal Stranding Hotline. They are, in a meaningful sense, the story becoming visible to the public in a form that the underlying data cannot. An oceanographic anomaly, expressed as a departure from the climatological mean in a sea surface temperature field, is not a story that most people can hold in their minds or feel in their gut. A walrus on a beach in Oregon, resting on sand that no Pacific walrus has rested on in any historical record, is a story. The challenge is in understanding what the story is actually about, because the walrus on the beach is not the beginning or the end of it. It is a symptom. It is the biological expression of a physical system undergoing a change whose consequences extend far beyond the individual animal and far beyond the beach where it has temporarily come to rest. The ocean temperature reading that precedes each Oregon walrus sighting is not interesting because it predicts the haul-out event in an operationally useful way. Wildlife managers cannot dispatch teams to intercept walruses before they arrive because the buoy data shows a warm anomaly. The temperature reading is interesting because it locates the haul-out event in a physical context that is larger than the event itself. It connects the walrus on the Oregon beach to the ice dynamics in the Chukchi Sea. It connects the ice dynamics in the Chukchi Sea to the heat content of the northeastern Pacific. It connects the heat content of the northeastern Pacific to the processes that are driving the long-term trajectory of the entire system. The temperature reading is the thread that, if you pull it, leads back to the conditions in the walrus's home range that are producing the behavioral disruption visible in Oregon. And the conditions in the walrus's home range lead back to the broader story about what is happening to the Arctic and to the ocean systems that are coupled to it. The regulatory framework governing Pacific walrus management in the United States runs primarily through the Marine Mammal Protection Act of 1972, which prohibits the harassment, hunting, capture, or killing of marine mammals in United States waters, except under specific permit conditions. The MUMPA provides baseline legal protection for the animals that appear on Oregon beaches, and the legal requirement for members of the public to maintain distance from holdout marine mammals applies to walruses as it does to pinnipeds of more familiar species. The U.S. Fish and Wildlife Service, which has jurisdiction over Pacific walruses, as opposed to NOAA Fisheries, which has jurisdiction over most other marine mammals, has been engaged in a protracted regulatory process regarding the Pacific walrus's status under the Endangered Species Act that has extended over more than a decade without reaching a formal listing. The species was found to warrant listing in 2011, meaning that the biological evidence supported the conclusion that the species faced threats to its survival. It was not listed, however, because other species in the listing queue were considered to face more immediate threats. It remained in a category of candidates for listing without formal ESA protection through the subsequent decade, a status that has been the subject of litigation and advocacy by conservation organizations that consider the biological evidence of threat to be sufficient to require the regulatory response that listing would trigger. The management complexity of a species that spends most of its life in international waters, that ranges across waters shared by the United States and Russia, that depends on sea ice dynamics driven by global atmospheric forcing well outside the regulatory authority of any single nation, is not trivial. The Pacific walrus does not live inside a jurisdiction in the way that a terrestrial species does. Protecting its habitat requires international cooperation on questions that are simultaneously scientific, diplomatic, and political, in ways that make the challenges of managing a terrestrial carnivore in a specific national forest look straightforward by comparison. The bilateral frameworks that govern joint management of transboundary marine resources between the United States and Russia have been strained by the geopolitical dynamics of the past decade in ways that are not productive for the collaborative scientific work that effective transboundary marine mammal management requires. The Alaska Native communities, whose subsistence rights to harvest Pacific walruses are protected under the MUMPA, have been among the most consistent and well-informed voices in the regulatory process, bringing observational knowledge and cultural stakes to a conversation that has too often been dominated by bureaucratic categories and litigation timelines. The population estimate uncertainty that characterizes Pacific walrus science is itself a reflection of the management challenge. Surveying a population of potentially 200,000 animals distributed across hundreds of thousands of square miles of remote Arctic ocean and coastline, at a latitude where aerial survey windows are limited by weather and light conditions, with individuals moving between ice platforms and open water on timescales shorter than survey intervals, is genuinely difficult. The confidence intervals around Pacific walrus population estimates are wide. The degree to which changes in population size could be detected against the background of survey uncertainty is limited. This means that a declining trend in the population, if one were occurring at the moderate rate that a gradual reduction in reproductive success and calf survival would produce, might not become apparent in survey data for years or decades after the underlying biological processes had begun producing the change. The signal would lag the reality. By the time the trend became statistically unambiguous in population survey data, the conditions driving the trend would have had years or decades to develop further. This lag between biological reality and statistical detectability is one of the most serious challenges in managing long-lived marine mammals, and it applies with particular force to a species as difficult to survey as the Pacific walrus. The parallel that keeps appearing in the scientific literature on Pacific walrus ecology, sometimes explicitly and sometimes by implication, is to the walrus's counterpart at the opposite pole. The Antarctic ecosystem, while not home to walruses, hosts seal and penguin species whose dependence on sea ice has produced well-documented population responses to sea ice changes that serve as cautionary case studies in what happens to ice-dependent species when the ice changes faster than the species can adapt. The Adelie penguin, whose distribution and reproductive success in the Antarctic Peninsula region have been tracked over decades of intensive study, has shown population declines in areas of the peninsula where sea ice has been most dramatically reduced, while increasing in areas where ice conditions remain favorable. The pattern is not uniform across the species, but the correlation between ice availability and Adelie penguin demographics in specific regions is robust enough to function as a predictive model. The Pacific walrus is not a penguin, and the Arctic is not the Antarctic Peninsula, but the fundamental dynamic, ice-dependent species encountering reduced ice availability and showing population responses distributed unevenly across the species range is the same. The management response that the Pacific walrus situation most urgently requires, and that is most clearly beyond the reach of conventional wildlife management tools, is the stabilization of the global temperature trajectory that is driving Arctic sea ice loss. This is a statement that is simultaneously obvious and almost completely unhelpful at the operational level of wildlife management, because the mechanisms through which global temperature is controlled are not wildlife management mechanisms. They are energy policy mechanisms, economic policy mechanisms, international diplomacy mechanisms. The Pacific walrus's fate is being determined in processes that have nothing to do with wildlife management and everything to do with the trajectory of global carbon emissions. This is a genuinely novel situation for wildlife conservation, which has historically operated on the premise that habitat can be protected through land acquisition, that threats can be reduced through regulatory intervention, that population dynamics can be influenced through harvest management. All of those tools are useful and important for Pacific walrus conservation. None of them address the primary driver of the threat the species faces. What wildlife management can do, and is doing, is monitor the population's response to changing conditions with sufficient rigor to detect demographic signals before they become irreversible, work with indigenous communities to integrate traditional ecological knowledge into the early warning system for population stress, manage the secondary threats that combine with climate impacts to compound the stress the population faces, specifically including disturbance at large haul-out sites and the potential for increased industrial activity in Arctic waters, as sea ice loss opens previously inaccessible areas to shipping and resource extraction, and engage in the habitat protection and planning processes that can reduce the rate at which walruses encounter additional stressors layered on top of the primary climate-driven ones. The walruses appearing on Oregon beaches fit into this picture as indicators, not of the failure of these management efforts, but of the degree to which the fundamental forcing that is driving the species' displacement from its historical range has advanced beyond what management tools designed for a stable climate can address. The animals are showing you something. They are not showing it in a language that is easy to translate into policy action. But the translation is possible if you understand what you are seeing, and what you are seeing when a Pacific walrus hauls out on an Oregon beach is an animal that has been displaced from conditions that the species has spent millions of years adapting to by changes that have occurred within a human lifetime. The question of what the Oregon coast looks like in another 20 years, in terms of the frequency of Pacific walrus sightings and the conditions that produce them, is not answerable with precision. The trajectory of global temperature, and therefore of Arctic sea ice, is contingent on human decisions that are being made now and will continue to be made across the coming decades. The range of possible futures for the Pacific walrus population is therefore genuinely wide. In scenarios where global temperature stabilization is achieved at or near the targets established in international climate agreements, the pace of Arctic sea ice loss slows significantly, and the walrus population faces a changed but potentially manageable new normal. In scenarios where emissions continue on a trajectory closer to current trends, the Arctic sea ice loss accelerates through additional feedback thresholds. The foraging and reproductive conditions for Pacific walruses deteriorate at a rate that the population's capacity for behavioral and demographic adaptation cannot match, and the Oregon haulouts become more frequent not because the Oregon coast has become walrus habitat, but because the displacement of the population from its historical range has become more severe. The ocean temperature reading off Newport, Oregon, on the day a Pacific walrus hauls out there is a number. It is a number produced by a sensor at a specific latitude and longitude, in a specific body of water, on a specific date. It is not, by itself, a narrative or an argument or a warning, but it is connected to other numbers, in other places, across other dates, through physical and biological linkages that are well understood, and when you trace those connections, the number off Newport resolves into something larger than itself. It resolves into a pattern. The pattern is the story of a physical system changing in ways that are displacing biological communities from the conditions they evolved in. The walrus is the part of that pattern you can photograph. The temperature is the part of that pattern that tells you what you are actually looking at. There is a version of the Pacific walrus story in which the Oregon haulouts are curiosities, charming encounters between surprised beachgoers and an improbable animal far from home. That version is not false. The encounters are, by any measure, remarkable. An animal of that size, that geographic origin, that ecological specificity, resting on a Pacific Northwest beach, is a sight that deserves the attention it gets. But the curiosity version of the story strips the event of the context that gives it meaning. The walrus on the Oregon beach is not lost. It is displaced. Those are different things. Being lost implies a navigational error relative to a destination that still exists as it always was. Being displaced implies that the conditions in the place the animal came from have changed in ways that are pushing it beyond the boundaries of its historical range, not because the animal has made an error, but because the world it evolved in has shifted beneath it. The sea ice that Pacific walruses have rested on for thousands of years, that has delivered them to the foraging grounds their bodies are built to exploit, that has supported the social aggregations in which calves are born and females nurse, and young males practice the behaviors they will depend on for decades of adult life, is retreating. Not uniformly, not at a constant rate, not without year-to-year variability that makes any specific year a poor basis for sweeping conclusions. But the long-term trend is not in the data range that can be called anything other than a retreat. The animals are responding. The behavioral responses are visible in the haul-out events at Point Ley and Rear Cape, and the other large terrestrial haul-out sites that have become fixtures of the annual news cycle from the Arctic. The behavioral responses are visible in the individual young males appearing in Washington and Oregon, and occasionally California. The oceanographic context for those responses is visible in the temperature anomaly maps and the buoy data, and the satellite-derived sea surface temperature fields that the scientific agencies publish in near real time, and that anyone with the inclination to look can access. The inclination to look is what matters. The data exists. The biological record exists. The connection between the temperature reading and the haul-out event, between the ocean state and the animal's displacement, between the displacement of the individual and the broader trajectory of the population, is traceable by anyone willing to trace it. The walrus on the beach is not a mystery. It is a question with a known answer, and the answer, when you follow it back through the oceanographic and ecological chain to its source, points to something that extends well beyond the natural history of a single charismatic species, and into the physics of a planet whose thermal balance has shifted measurably within the span of a human lifetime. The animal is showing you that. The ocean temperature is confirming it. Whether either of those things produces the kind of attention that translates into meaningful action is a different question, and the answer to it is not written in the data. The data can only tell you what is happening. What happens next is still, at least partially, a human decision. There are roughly 35 miles of sandy beach on the Oregon coast, south of Tillamook Head, that have produced confirmed Pacific walrus sightings in the period since 2010. None of those beaches are in the Pacific walruses range. None of them have the benthic prey communities that could sustain a walrus. None of them are covered with sea ice in winter. None of them are anything like what a Pacific walrus's biology is calibrated for. The animals that have rested there, hours or days at a stretch, before returning to the ocean, have done so because the conditions that would ordinarily constrain their movements to waters thousands of miles to the north and west have been progressively loosened by a cascade of changes that began in the atmosphere and expressed themselves in the ocean and arrived at the beach in the form of an animal that should not be there. When the next one arrives, and the trend suggests there will be a next one, the ocean off that beach will almost certainly be running warmer than average. The buoy will say so. The satellite temperature maps will say so. The historical record of the events that have preceded each Oregon walrus sighting will say so. The question is whether, this time, the reading gets connected to what it means.